Today, in this lecture, we will see numerical. Numerical is a bar of cross section 8 mm by 8 mm is subjected to axial pull of 10 kN. The lateral dimensions of the bar are found to be reduced by 2 into 10 raised to minus 3 mm. Find Poisson's ratio and modulus of elasticity. And in numerical, they have given us G, capital G, that means shear modulus, is equal to 80 MPa. First, draw a bar of cross section axial pull 10 kilonewton. And a bar of cross section, this side of bar is width and this is thickness. See this x-axis, y-axis and z-axis. This 10 kilonewton axial pull acting on x-axis, and this x-axis is longitudinal direction of this bar, and this y and z-axis are lateral directions. So and we have to find Poisson's ratio and modulus of elasticity. First write given data. Capital A is equal to 8 mm by 8 mm. A means area of that cross section of bar is 8 mm by 8 mm. 64 mm square. P, load axial pull acting on this bar is 10 kilonewton. Ten into 10 raised to 3 Newton. The lateral dimensions of the bar to be reduced by 2 into 10 raised to minus 3 mm. Lateral dimensions of this bar are this y-axis and z-axis. This vertical y-axis and z-axis. This T thickness is lateral dimension of this bar. So change in thickness is equal to two into 10 raised to minus 3 mm. Shear modulus is 80 GPa. That means 80 into 10 raised to 3 MPa. And to find Poisson's ratio and modulus of elasticity. For finding this Poisson's ratio, first we find lateral strain. After this lateral strain, we find linear strain. After this, stress and modulus of elasticity. And by using the relationship between E and G, we find this mu, Poisson's ratio. We will see step by step this. First, understand numerical. A bar of cross section 8 mm by 8 mm is subjected to axial pull. The lateral dimensions of the bar are found to be reduced by 2 into 10 raised to minus 3 mm. Find Poisson's ratio and modulus of elasticity. They have given us in numerical. Shear modulus is 80 MPa. Area of that cross sectional bar is 64 mm square. Load acting on this axial load acting on this cross sectional bar P is equal to 10 kilonewton. Change in lateral dimensions is 2 into 10 raised to minus 3 mm. Shear modulus is 80 GPa, that means 80 into 10 raised to 3 MPa, and we have to find mu and E. See, by using this area, this P load, this change in lateral dimension and shear modulus, we have to find mu and E. And we have formula for relationship between this mu E and G, but only one term is not acceptable for this finding this modulus of elasticity. See this formula, E is equal to 2G in bracket 1 plus mu. We have G, but we don't have mu. So first find this Poisson's ratio, and after finding this Poisson's ratio, we find this E. Okay, we will see it step by step. For finding this mu, first we need lateral strain. Lateral strain is denoted by EL, strain is denoted by E, and here this L for lateral, EL lateral strain. EL is equal to lateral strain is change in thickness to the original thickness. In numerical they have given us change in thickness is 2 into 10 raised to minus 3 mm, and this T also they given us in numerical, this T is 8 mm. So see, this change in thickness is 2 into 10 raised to minus 3 upon this thickness is 8 mm. So find 2 into 10 raised to minus 3 upon 8, 2.5 into 10 raised to minus 4. EL, and strain have no unit. Next, find linear strain. Linear strain E, and linear strain is, so see, by finding linear strain we use Poisson's ratio formula, and this Poisson's ratio is lateral strain to the linear strain. See this lateral strain EL to linear strain E. Therefore E is equal to EL upon mu. And in step 1 we find lateral strain is 2.5 into 10 raised to minus 4 upon mu E. Our interest is to find this Poisson's ratio, and after this Poisson's ratio we find modulus of elasticity. So for finding this Poisson's ratio we also need stress. Stress is denoted by sigma, and sigma is equal to load upon area. Stress is load upon area, and load is 10 into 10 raised to 3 Newton, and area is this 8 mm by 8 mm, 64 mm square. Stress is 156.25 Newton per mm square. Next step for modulus of elasticity. Modulus of elasticity is stress upon strain. And stress is 156.25 and strain. The strain is 2.5 into 10 raised to minus 4 upon mu. This is E. See, this 156.25 upon 2.5 into 10 raised to minus 4 is 625 into E is equal to 625 into 10 raised to 3 mu. Next, Step 5. Using relationship between E and G, we find mu. See, this is 625 into 10 raised to 3 mu is equal to 2G. This G is, see in numerical, G is 80 into 10 raised to 3 and 1 plus mu. See, 625 into 10 raised to 3 into mu is equal to mu is 0.344. This mu Poisson's ratio is 0.344 and see this E here. E is equal to 625 into 10 raised to 3 into mu. Therefore, E is equal to 625 into 10 raised to 3 into mu is equal to 625 into 10 raised to 3 into mu is 0.344. 625 into 10 raised to 3 into mu is 0.344. 215 into 10 raised to 3. Newton per mm square. This is and mu. We find this. Okay. C. Bar subjected to 10 kN axial load. B and T are 8 mm. X is longitudinal direction and Y and Z are lateral directions. Change in lateral direction is 2 into 10 raised to minus 3 mm. Shear modulus 80 into 10 raised to 3 MPa. And we have to find Poisson's ratio and modulus of elasticity. So for that, first we find lateral strain. Lateral strain is 2.5 into 10 raised to minus 4. After this lateral strain, by using lateral strain, we find this linear strain. And for finding this linear strain, we use formula of Poisson's ratio. Next, we use stress formula. Why I write here stress formula? Because in this modulus of elasticity equation, we need stress. Stress upon strain. By using stress upon strain is equal to modulus of elasticity, we get modulus of elasticity is equal to 625 into 10 raised to 3 mu. And using relationship between modulus of elasticity and shear modulus, we find this mu Poisson's ratio is equal to 0.344 and modulus of elasticity is 215 into 10 raised to 3 Newton per mm square. Okay, thank you very much.